Today we're going to learn about jumps and branches, but before we do, I'd like to just do a little bit of a revision about how a MIPS program is structured and the cycle of execution. So if you remember from earlier, we said that MIPS uses specific areas for specific areas of memory for specific uses. So the program or the machine code instructions and the data use distinct areas of memory. So when you assemble your code, it gets changed into machine code instructions, and then it gets loaded into the area of memory reserved for program text, and then your program counter goes through that. How does it go through that? Well, that's the fetch, execute, or fetch, decode, execute cycle. The control unit repeatedly fetches the word at the address given by the program counter. At that address, there is a machine code instruction as a word. So for example, the bottom down there we've got 004001A8, and that takes us to an address, and at that address, using little endian, the word is 0338C820. Then once we have that machine code instruction, we have to decode it and figure out what it does. So then we see that that corresponds to an add instruction using a couple of registers. And once we have that, we then execute the instruction. And that means we need to load the data from memory into registers, perform the ALU operations, and then store the data back into memory. And now, something that's going to be a key idea in this lecture is that we then update the program counter, usually by incrementing to the next instruction. So you can see at the bottom there, the program counter is going from A8 to AC, and that's because we increment by 4 to get to the next word stored in memory. So usually you just increment and increment and increment, and that means that we just do one thing after the other. We just keep on doing instructions until we run out of instructions to do or we're told to quit. That's because assembly language is unstructured, so there's no modularity, no functions, no methods, no code blocks, no scoping, no classes, no objects, no types. There's a whole lot of nothing. There's a whole lot of just instructions that you have to execute one after the other, and that's all you do until you start using branching and jumping instructions. Now there's quite a lot here, so I wouldn't expect you to learn all of these. I would expect that after this week you'll be able to use most of these, even if you don't know that they're instructions off by heart, because you'll always have your MIPS summary sheet. But basically, they take a label, and a label tells them where to go. And but before we get onto that, let's have a little think about the difference between jumping and branching. So jumping, and in this case an unconditional jump, just takes a label and sets the program counter equal to the memory address of that label. So remember from our assembling code video that when we assemble a program, labels get given a memory address and it corresponds to the next instruction after that label. So if we jump to a label, really what we're doing is saying is go to this memory location, and here there will be an instruction that you can execute. So down here we've got jump to L2, and that just sets the program counter to be equal to L2's memory address, and then jump to L1 takes us right back up to the top where that memory address is stolen. So these are unconditional. These are just go to here no matter what. The other side of that coin is branching. Branches use a condition. In this case up at the top here we've got branch if equal, which says set the program counter equal to the label L if the registers R and S are equal to each other. So you could think of this kind of like an if statement, and it's similar. It's not quite the same thing because, well, we'll get onto that, but it's a similar concept. So what branches say is if a condition takes hold, or if a condition holds and is true, take the branch, otherwise just move to the next instruction. So unlike jumping where we just go to the label, branching allows you to give it a label which it might take if a condition holds, otherwise it will just carry on as before. So here we have branch of equal T0, T1, L2, so if the contents of T0 and T1 are not the same, then it'll just carry on. If they are the same, then it'll jump to L2. And down at the bottom we've got branch of less than 0, so if S7 is less than 0, we'll jump to L1, otherwise we'll stop and just carry on down the bottom. So let's have a think about how this would relate to an if statement. So here up at the top we've got if A is greater than B, A equals A minus B, and C equals A plus B. So how would we convert this into MIPS? Well, we'd use branch of less than or equal. So that's saying if A is not larger than B, then jump. So if the if condition is not met, jump past the if condition. So we kind of have to specify it in the opposite way here, where we're saying that if that condition is not met by this meeting another condition, then we jump on. Otherwise, we just fall down. If A is bigger than B, if it doesn't meet that criteria branch of less than equal, then we just drop down and do the subtraction. Otherwise, we jump forward. But you'll notice here this is set up so that we also carry out the add instruction either way, because if we don't pass the branching condition and we just go to the subtraction, we still then go on to the add condition, much like the if statement up there. So one thing that might be more useful is comparison instructions, because previously, as that previous example showed, that we used the opposite argument. So rather than saying it's greater, we tested to see if it was less than or equal to and jumped on that condition, which is the opposite. You can use comparison instructions. Now, comparison instructions allow you to just specify the instruction directly, as it might not be feasible to do that using a branch condition. But what I'd like you to look at here is this slightly odd notation on the right hand side, which tells you the behavior of the comparison instruction. Now, it might seem odd, but if we go down to this bottom if statement where we have if A is greater than B, max equals A, else max equals B, the way we would specify that using the notation on the top right there is max equals and the condition, and based on that condition we would say A or B. So if A is bigger than B, you would read that as max is equal to, if the condition A is greater than B, then it should be A, if not, then B. So up at the top here in our set equal, it says R is equal to, and then you test to see that if S is equal to T, you set 1. If that condition fails, you set 0. So you can just read it as, if the condition passes, the first thing happens, otherwise the second thing happens. But let's have a look at how we might use this. So this is the same if statement. So what we could use instead of just the branching instruction is set greater than, which says if S1 is greater than S2, then set T0 to 1. Otherwise, set it to 0. And then, because you've set this register T0 to be equal to the result of that logical test, you can branch if equal to 0. So if that condition didn't get met and the 0 is set in T0, then you will jump. If it is met and the 1 is set, then you won't jump and you'll fall through. So what are the advantages to this? Well, your comparison now matches the condition because you're directly checking if A is greater than B, which is a good thing. And the branch instruction is always B equals Z, branch if equal to 0, because you're always testing if it's a 1 or a 0. So you get rid of some of the ambiguity about which branch instruction you might want to use, and that can be helpful. And it's simpler for more complex conditions. However, it does require an instruction in the register that you otherwise wouldn't use, because you have to use this intermediate register to store the result of your logical test, whereas beforehand you would just use your branching instruction. So depending on the situation, you might want to use this, you might not. Now let's have a look at some more complex conditions. So here we have if A is less than 0 or A is greater than or equal to 0, we do the out of range, and then we move on. So how would we mimic this using MIPS? Well, we can use the set less than immediate value, which is set to say if the value in S1 is less than the immediate value we get. So in this case we're saying if S1 is less than 0, set T0 to be equal to 1. And then we can also say set greater than or equal to S1 and 16. So we can use a hard-coded value there as well to say, or if A is greater than or equal to 16, store that bit in T1. And then we can just use the logical OR condition to say if either T0 or T1 is set, I want you to OR that. So if either one is set, we'll get a 1. If both are set, we'll get a 1. If neither is set, we'll get a 0. And then we can branch if equal to 0 again. So, and you just have to split the condition up into more smaller subcomponents to do this. So let's have a look at another example. So let's say if we were doing the opposite and we wanted to see if it's in the range. So what we could do is we could immediately test to say branch if less than 0. So if A fails, if A fails to be within the range by being less than 0, we can just jump immediately, because in this case it's an AND condition, so we don't have to check both conditions. We can just check that either one fails because it's an AND. So if one fails, they both fail. So that's fine. So if branch less than 0 says If a is less than 0, then we skip. We go to skip in range because it's not in range, so we can't do that bit of code. And then we can use branch greater than or equal to say if S1 is bigger than 16, then we're also not in range, so jump to the skip in range command. So hopefully that's clear, I hope. Let's have a look at some if else conditions. So if a is greater than b, then we do a equals a minus b, else we want to do b equals b minus a, and then we do c equals a plus b either way. So let's have a look at this. So we can do BLE again, say branch less than or equal to, so if it's not the case that a is greater than b, we can just jump to the else block using a branching instruction. So if the condition fails to meet the if condition, then we just jump to the else block and do that instruction. Now, if we meet the if condition, so if a is greater than b, and our branch fails, then we would do the subtraction, but then we would want to jump because we don't want to fall into the else statement, which would happen if we don't have a jump there. So we want to jump unconditionally to the end of the if statement to do that addition. And this is very important because without this jump, we would just go straight into the else block because the program counter would just get updated and we would wind up at the else block and do that subtraction anyway if we don't have the jump. So you need to remember to jump over the stuff you don't want to do. However, if the BLE condition is met and we jump to the else block, we can just do the subtraction and we don't need to jump to the end if, because in that case when we're in the else block, the program counter will be updated and we will just fall to the end if statement anyway, so we don't need to worry about jumping in that case. Okay, I hope this was useful for you. This is quite, I think some of this stuff can be quite tricky, so if you have any questions, please do let me know. Otherwise, thanks for listening. Bye.